Hi everyone. Our research paper is titled Managed Communication and Consistency for Fast Data Parallel Iterative Analysis. The authors of our paper are affiliated with the Carnegie Mellon University, Institute for Infocom Research, A*STAR, and Intel Labs. So processing data in parallel is very important in machine learning because the data set the data set will be very huge. So the authors created a system called Boson. The parameters of the model are refined by iteratively processing the training set until convergence, and we will go over convergence in the next few slides. The quality of the model depends on the quality of the refinement. So some background on the Boson system. So the authors define Boson as a system that maximizes the network communication efficiency under a given inter-machine network bandwidth budget to minimize parallel error, while ensuring theoretical convergence guarantees for large-scale data paralleled machine learning applications. So we have to maximize the parallelism while minimizing the errors because errors can cause delays in completion and inaccuracy in the overall quality of the refinement. So some key features of Boson. So convergence means when the parameters are close enough to an optimum. So theoretical convergence is guaranteed with Boson because it utilizes the bounded staleness consistency model. So the bounded staleness parallelization is when each worker has a stale local copy of some model A, where the staleness is bounded by some threshold value S. That's the positive integer that the user inputs. And no other worker is allowed to be more than S clock units ahead of the slowest worker. So this, the Boson system it utilizes the bounded staleness consistency model, but the consistency model is not a new model. It's already been established. So this system overall can't be considered new because there's marginal novelty. The Boson system maximizes the network bandwidth efficiency, and it's the first distributed implementation of adaptive revision algorithm. So in this diagram, we can go over the bounded staleness. So here we have 5 workers, and the staleness threshold is 3, so S equals 3. As you can see, worker 2 is currently running on iteration 4. So it's guaranteed to observe all the updates generated before 4 minus 3, so that's 1. So until here, it has all the updates. And then worker 2, it might observe the local updates in green. And then the updates that are generated in completed iterations by other works, so other workers, so worker 3, worker 4, worker 5, that might also be visible since they are propagated at the end of each clock. And the updates generated in incomplete iterations, so all these white fields, they're not visible because they're not communicated yet. So because the staleness threshold is 3, worker 2 is blocked because worker 2 is blocked until worker 1 reaches clock 2. So if a worker proceeds any further, then it crosses this threshold. So that's why worker 2 is blocked. So the Boson architecture, it consists of a client library and the parameter server partitions. The purpose of the client library is to provide the API for reading and updating the model parameters. And the purpose for the parameter server partition is that it stores and maintains the model A. This architecture utilizes a key value mechanism where the machine learning program process is linked to a client library, and any thread in that process can read or update the model parameters concurrently. The client library and the server partitions, they also have a consistency manager that enforces the stillness threshold. It communicates as many updates per second as possible without overusing the bandwidth. The communication manager regularly checks if the network is being overused by monitoring the messages sent without acknowledgement. And if there are too many messages that are sent without acknowledgement, then the messages are halted until it sees that the bandwidth is clear. It also prioritizes more important model updates to improve machine learning process per iteration. So it needs to pick the right prioritization strategy, the randomized, round robin, or relative magnitude. The Boson system provides fault tolerance by checkpointing the server model partitions. So in case there is any failure, then the server starts from the last checkpoint that was taken. And it considers a valid checkpoint as it includes all the model updates before and during iteration T, and excludes all updates after the TS clock called by any worker thread. And the checkpoint is not created every iteration. The one downside to this method for fault tolerance is that it's a very expensive operation. So the Boson client API is easy to use because, as you can see, it's like it has the get row, the increment the row clock function. So they're pretty simple to use. And to fully utilize locality in machine learning applications and reduce any overhead in operating concurrent data structures and network messaging, the parameters are statically partitioned into batches called rows, and each set of parameters in the row can be accessed together, and it is what is used to communicate between the client and the server.
The Boson is tested by the author on 3 commonly used machine learning programs. The first one is metrics factorization, which is used by Netflix to create a movie recommender system. For the experiment, the author uses input data from Netflix, which contains observed ratings from multiple users on multiple movies. And all the experiments in metrics factorization use adaptive revision, meaning that the updates are first calculated by the server according to step size rather than directly applied to the parameter. The second machine learning program is multi-class logistic regression. This program is used in large-scale classification, such as natural language processing or click-through rate prediction. The data set chosen for MLR is from ImageNet, containing 1,000 class label with 21,000 features. The third one is topic modeling. It is an unsupervised method to uncover hidden topics from a group of documents. It analyzes words in documents to create word topic vector to represent words mentioned in specific topic. And a second vector which collects something similar, but is instead related to the whole document rather than individual words. And the third vector calculates number of tokens in the document assigned to specified topic. And now let's move on to the evaluation. The hardware setup involves 2 kinds of cluster for the evaluation. The first one is Probe GNOME cluster. It contains 200 high-end computer running Ubuntu. And each of them carry 4 quad-core CPUs, which is 16 physical cores per machine, and 32 gigs of RAMs. The machines are distributed over multiple racks and are connected using 1 gigabits of Ethernet and 20 gigabits of InfiniBand. However, in the experiments, only 8 to 26 T4 of machines were used. within this cluster. The application that runs on this cluster includes the MF with Netflix database, the recommender system, and LDA with New York Times, and LDA with ClueWeb. Both of New York Times and ClueWeb provide documents. One is article and one is web page. The second cluster is this cluster featuring a higher-end machine with 64 physical cores and 128 gig of RAM. The machine in the cluster is distributed over 2 racks and are connected with 2 networks, 1 gigabit Ethernet and 40 gigabit Ethernet. There's only one application that is evaluated on this cluster, which is the MUR with ImageNet dataset that classifies image over 1,000 class. In the experiment, 4 machines are used. On both of these clusters, server and client are collected and evenly distributed, and data are partitioned across worker evenly also. The performance of the particular system setup is measured by how fast the same machine learning program running on top can reach a certain objective value, meaning how fast the machine learning program learns. So the first system setup author tested is communication management. To know how much improvement network bandwidth can create, metrics factorization and LDA is tested under different network bandwidth settings. So from the figure on the left representing MF, in order to reach the same objective value 2E7, which is the line from here, which is this point, this horizontal line. The line isn't very straight, but that line indicates the objective value that a machine learning algorithm should approach. And from the figure, the bonded stillness uses 24 iteration, while managed communication with 200 megabits of bandwidth reduces the iteration down to 24. On the right-hand side, the figure represents LDA machine learning application. To reach the same convergent value, BS uses 740 iterations compared to MC320R uses only 195. And further, while using 640 megabits of bandwidth network, it reduced the iteration needed to 120. But these two figures shows that when given a higher bandwidth using Bowden system, executing bonded stillness and managed communication can speed up a training process compared to simply using bonded stillness system only. The second variable paper talks about is how prioritizing the message can affect the training speed. On the same figure, managed communication over 320 megabits network has a different performance when choosing prioritization method of relative magnitude and randomization, which is the R and RM at the end of the label. And relative magnitude outperform randomization in both 320 megabits per second network and 640 megabits per second network setting. The improvement of relative magnitude compared to randomization is that it differentiates update and model parameters based on their significance to algorithm performance. In other words, RM tend to use network bandwidth with message that has more impact on the algorithm, and the result shows that it has achieved its purpose. Based on the result of prioritization and managed communication seems that with better message control over network, machine learning can achieve better performance without drawback, simply from increasing bandwidth higher and higher. And however, there is some drawback while utilizing larger network bandwidth. The problem is the CPU overhead. The overhead of CPU handling network content happens when higher bandwidth is in use. The CPU usage compared MC in 200 randomization is 12% more than simply using bounded stillness. And both metrics, factorization and LDA, shows similar growth of CPU usage when having higher network bandwidth. But on the other hand, the performance growth from increasing network bandwidth is significant too. Using a bandwidth of 800 megabits per second comparing to no managed control bounded stillness system, the 800 megabits per second system shows large improvement to a 2.5 times faster in wall clock time. And from bandwidth control to prioritizing message, another way to improve algorithm performance is to reduce parallel arrow. And one way to reduce the parallel arrow is to reduce data paths into multiple clock ticks to achieve more frequent synchronization. The paper compared clock tick size tuning in LDA to bandwidth control, and results in LDA increases network consumption significantly when it tries to reduce clock tick size. But it also shortened the time the LDA needed to converge. But the author proposed that when using managed communication, it actually outperformed the clock ticking tuning while using less bandwidth. So it only used 63% of bandwidth comparing to LDA, but it achieves a faster conversion rate, about 28%. However, there is some limitations to the boson system. For the boson system to work at maximum bandwidth utilization, first of all, the network of every node is assumed to have the same inbound and outbound bandwidth. Also, it assumes each node's inbound and outbound bandwidth is evenly shared with all the nodes that it is communicating with. But both of the assumptions are broken in today's hierarchical network topology, and it might lead to underutilized network bandwidth. To summarize the evaluation, bounded stillness reduces communication for machine learning algorithms, but there is a possibility that accumulated error may happen and lead to slower convergence rate. Like boson system, by increasing the communication, we can reduce that error. And using a well-managed communication comparing to pure bound stillness achieves a 2 to 3 times speed up. But there is a limitation to the physical network. The network system proposed in this paper is specially designed to distribute network within maximum bandwidth, which every node shares its inbound and outbound bandwidth evenly to every other node it communicates with. So in real-world data center, the network architecture may cause the bandwidth to be underutilization, which we should keep in mind if we implement the proposed method in the application. And that summarizes our experiment. Thank you for listening.